Welcome everyone to this new SIPTA seminars. So you can see the title of the seminar for the moment. We will come to it in a few seconds. But okay, before starting the seminars, we thought with the organizers of the seminar that we had to pay homage and tribute to someone who recently passed away. So for those of you that didn't know, unfortunately, Thomas Augustine, who was a real pillar of our community, both from the scientific side and the human side. I think it is one of the kindest and most generous person I ever known as a scientist. So it's sure that in the community we will all surely miss him. And if you want to pay an homage to Thomas, you can put a message on the LMU memorial. And if you want to know more about the career of Thomas, we did with the society a small obituary made by some of his previous and current students. So if you want to honor Thomas, this is certainly a way of doing it. We'll try to do different ways to do it, but I'm sure we will all remember him with fond memories. Okay. Now, for the scientific part that I'm certain Thomas would have liked, we will receive today a talk done by E.Goubault and Pifarré-Esquerda, and also Sylvie Puteaux. She will not be talking, but she's a big part of this work, I would say, and she's also in the audience. And this will be about a Dempster-Shafer approach to the quantitative verification of neural networks. So a very, very trendy topic. But Eric and Sylvie have worked for a long time on the verification on physical cyber systems and on all kinds of systems using, I would say, mostly set theory, but also very, not so recently, because I will also be sharing the session. I came on Eric and Sylvie works quite some years ago, and I always thought, oh, this is very nice work, so I should know more about it. So the way I managed to know more about it was to invite Eric and Sylvie to give a talk at our laboratory, since they were working on imprecise probabilities, and we love imprecise probabilities where I work. So they came to make a fantastic seminar to our laboratory. They were also very nice people. We had a very nice lunch talking about IP, but other things. And I thought, okay, it would be a very good idea to make the work of Eric, Sylvie, and I think one of their newest PhD students, so with Francesc, to talk to us about IP in general and apply to the verification of systems. And here neural networks, but I think Eric will touch about the bigger picture. So I'm certain this will be an interesting talk because I've seen something similar before it. And I invite you all to listen to Eric. So Eric, I'm very glad that you and Sylvie and Francesc accepted to do this talk. And I leave you the floor.
Okay, thanks a lot, Sébastien. So we remember very nicely this invitation of yours. It was indeed very nice to talk in Compiègne. So we are verification people. Ultimately, we're interested in checking various systems, as you said, and in particular these so-called CPS, cyber physical systems. So I'll start by sort of giving the bigger picture, as you mentioned again. And after that, I'll show how to use some basic imprecise probabilities to approach these verification problems. I'll just do the first easy part, and then I'll let Francesc do the hard part, right? No pressure, Francesc. Okay, so the context is that of it's so-called CPS, which are large systems which are everywhere nowadays, which are sort of distributed control systems and which definitely need high confidence, hence formal methods and verification. So I won't go through all the systems you can find on this slide, but rather go to the sort of promised autonomous car that probably nobody has right now, but which seems like fun. So we're promised these cars which would drive by themselves, and indeed what they should be doing is to have a good perception of the physical world. You see on the left LiDAR image of the obstacles. So find these obstacles, classify them, and then go through a closed control loop, a classical closed control loop mechanism to determine motion planning, so trajectories, and do low-level control and so on, okay? And more of these systems are actually done by neural networks, hence my the fact that I speak mostly about neural networks today. So, for instance, perception has long been done using neural networks, right? But more and more, everything actually. So sometimes you find even end-to-end learning algorithms which go from the video stream to or the LiDAR stream to directly controlling the angle of the steering wheel and the motor and everything. Okay. Mathematically speaking, this means that you have a closed loop, as I was mentioning. You'd have the physical world generally modeled by ODEs and a bunch of sensors, maybe neural networks for perception, and then planning and control, which could be using classical PID or optimal control, but also neural networks, and then commands to actuators and all to some time period. And ultimately want to check that. Okay, so there's been a lot of work we've been doing and others been doing on the physical part, on the control part, but once again, I'm concentrating on the neural network part, which will be mostly simple feed-forward neural networks or perceptrons. So these are composed of, so a first layer, which is just going to be inputs. Just think of pixels of an image, for instance. Then linear layers, transforming with given weights and biases linearly or in an affine manner these values, and then some nonlinear activation function f, and once again a pair of linear and activation function layers. So these activation functions, they can be differentiable, like sigmoid and hyperbolic tangent, but they can also be non-differentiable, at least everywhere, like the ReLU. And I'll be concentrated in the first part on the ReLU function. Francesc will do other activation functions as well, but that will be for later. So ReLU is just the maximum of 0 on its inputs. It has this graph, as you can see here. And the problem, of course, for verification people like us is to know whether this works correctly. You don't want to kill the driver. So unfortunately, currently it's a bit appalling what can happen. I won't show you the videos. You can find them on YouTube. But in this video on the left, you have a clear view on the road, right? But then suddenly the control loop decides, and the neural network basically decides to go towards the tree. And fortunately, the driver can take over the control back and is safe. Unfortunately, on the right-hand side, the driver is killed. The Tesla actually goes straight onto a truck which is stopped on the lane. Okay, but it's more foggy. You can probably better understand what's going on the right-hand side. But still, these two cases are probably instances of a classical problem that you have probably seen on the last CIPTA seminar, actually, which is robustness properties of the decisions of these neural networks, and it's linked to so-called adversarial attacks. So it's really a 7 mistakes game, right? But if you find a mistake by yourself, I'd be very surprised, because the difference between these two images is very small. It shouldn't be visible to the human eye. You see this noise on the right, which is scaled up a lot. And somehow the classifier sees the left one as a pig with a 91% confidence, and the one in the middle as an aircraft, let's say. The ears are probably seen as wings of some kind, okay? And definitely that's the first kind of property you want to check when you are into verification, into formal methods. So robustness is just trying to see if when images are close enough, image is prime minus image, can you check that at least if it's the noise is sufficiently small, can you check that image prime is classified as image, as a pig in that case, okay? So it needs to, for verification, to be able at least to propagate sets of values somehow. What would be the output of the neural network which makes decisions on a little ball around image? That's what we're going to see. So sometimes you are lucky, not like for image classification, because you don't have any specifications for a peak, for instance. So you cannot specify logically what you want to verify. But sometimes you're lucky, and we'll see another example, which is the ACAS, the Aircraft Collision Avoidance System, which has some specifications, formal ones, which we can check. But there again, it will rely on some sort of set-based methods and on bounds on what the decision might be on sets of inputs. And in the larger context of CPS verification, we're kind of lucky because although we cannot really formally specify what the low-level controller replaced by a neural network should be doing, we can at least specify what the full feedback loop should be doing, like stability properties, invariant properties, which are again set sort of properties, okay, which will require some set propagation through the system. Okay, so that's where I want to go right now. We'll be using some sort of reachability-based verification, at least trying to propagate sets of values or sets of trajectories through the system, at least in a bounded time manner, sometimes in an unbounded time manner, but that's for another talk, I guess. And of course, that is not even feasible algorithmically, because this set of values of neurons or this set of trajectories, they can't be described algorithmically. So we'll be trying to find generally approximations, inner and outer approximations, at least when it comes to non-probabilistic verification. And then I'll tell you about probabilistic verification a bit later, okay? Okay, so precisely my point now. Let's concentrate on neural networks and this idea of propagating sets of values. So suppose we have a tractable way to represent sets of values, like these boxes on the left for the inputs, and then that we are able to outer approximate the sets of values in the blue hidden layers in there, still using some kind of polyhedra, for instance. Ultimately, we can try to check whether the output, which will be outer approximated, is not touching an error zone, touching some decision boundary, which would transform the decision into something we wouldn't like to be, okay? That's typically what we've been doing, what others have been doing in this so-called qualitative verification framework. You will just prove that a given property is true or false or unknown. In case the outer approximation is both on the right side and the wrong side of the error zone, you will have to say it's unknown, right? Okay, but then this sort of qualitative approach to verification has its drawbacks, because precisely what I said, sometimes you cannot decide, and sometimes you cannot decide just because the system won't work always. You just imagine an autonomous car. There might be events with very low probability, which are impossible to get out from, and you'll certainly crash, right? What you want to know is the probability of you crashing, and ensure that this will be extremely small and probably just due to events you cannot control. So these events may be noises, for instance, on sensors, as we've seen for robustness issues. And these noises, they probably cannot be represented exactly by a probability, or at least some noises will be will just have bounds on them, not probabilities, and some other noises you might have the information that they are Gaussian, right? And you want to mix them together. So ultimately, you'll have to use some sort of imprecise probability framework. So typically, we might think that a sensor might have a noisy output of a Gaussian nature, but with an uncertain mean, because it can sense different things, right? Perhaps with a unique variance, or probably with an uncertain variance, okay? All sorts of possibilities there. Okay, hence imprecise probabilities. And I'll start first by looking at the obvious thing, using p-boxes and Dempster-Shafer structures on intervals, how it would go on neural networks. then slightly criticize that and improve it, and then leave Francesc do even better things, okay? When comparing our stuff, I'll be comparing it to something which is a state-of-the-art as well in verification, which is called ProbStar, which has also this idea of propagating sets and so on. So just to show you that we will be improving on state-of-the-art verification techniques. Okay, so the general framework for quantitative verification, for probabilistic verification of this system will be this so-called constrained probabilistic sets, typically to prescribe at least what are the possible distributions and support of the inputs to the neural networks we want to check. So you recognize already that we have some kind of p-box constraint on the input distributions for the neural network and the verification. And we'll have also some polyhedric constraint on the support of the distributions in that p-box, okay? That's a matrix C and a vector D here. And the problem we are going to try to tackle, which is the basic block for all further kinds of robustness verifications or verifying specifications, is to be able to, given such constrained probabilistic input set, find a similar constrained probabilistic set for the output and check on it, find on it bounds, probabilistic bounds on the safety property we want to check of the form hy less or equal than w, h being a matrix and w being a vector. So still in this idea of this error zone, which was going into different half spaces. So there again, I remind you, in that first part, I'm dealing with ReLU activation functions. And just to show you some ideas of what we're doing, this is just a toy example, which Francesc will be using again at some point. Just one hidden layer network, inputs between -2 and 2, -1 and 1. Want to check the property that the output neuron, the first one, is less than -2, and the second output neuron should be greater than 2. Indeed, the qualitative verification problem just asks whether it's always true for these inputs that these outputs satisfy these two inequalities, but we'll be interested in quantitative problems which are to determine at least bounds on the probability that these properties on the outputs are true, given that the inputs are, for instance, in uniform distributions between -2 and 2, or that they are normal Gaussian distributions with fixed mean value for one and uncertain variance for the first one, and uncertain mean and strict variance for the second, for instance. Okay, so first of all, I'll just show how one could naively do things using sort of naive, imprecise probabilistic approach, just using the idea that we start with some form of p-boxes, right? These probabilistic constraint input sets, they are particularly p-boxes, and in terms of computationally tractable ways to do imprecise probability propagation, we could use Dempster-Shafer structures on intervals. So we could model, for instance, this probabilistic constraint input set as DSI with a certain number of intervals as focal elements, a certain number of weights associated to these focal elements, and indeed there would be a way to represent particular staircase shaped p-boxes that you know how to determine from this DSI. And when we have exact distributions, as in ProbStar actually, against which we are going to discuss our results, then because they have been considering only multidimensional Gaussian inputs as distributions, right? So we'll be still approximating these exact distributions as inputs as particular discretizations as DSIs, as you can see in these pictures, when these have uncertain mean. Of course, you'll produce something a bit wider as shown on the right, okay? So as you know as well, there's an arithmetic on these DSIs, and at least you can have easily, for instance, the addition of two DSIs under the condition that they are independent probability distributions. Okay, so you'd find something fairly precise in this case for x plus y, as you show, as I show in the middle picture. And you can have also the more extreme sort of copula that you can get on x and y, which would be unknown dependency. And of course, what you will get is a much wider p-box or DSI containing all possible resulting set of distributions for x plus y. Okay, so just as a reminder, similarly for normal laws and other kinds of input distributions. So of course, for the linear layers, all the arithmetic is known, so we could use that. We just have to interpret the activation function, and for the ReLU activation function, it's very simple, just sort of cuts the p-box, the CDFs there in an obvious manner, and for the DSI, just is the result of applying the activation function on the focal elements, each one of these focal elements separately. So you can see that we replace after ReLU the focal element underline xi overline xi by max of 0 of underline xi and max of 0 overline xi. And for sigmoids and stuff, we could do similar things, of course. And well, you can just propagate using this plain arithmetic on DSI plus ReLU interpretation for all layers and see what you get. And at the end, interpret the CDF on the specification, find the probability bounds from there. So on the toy example, for instance, if you start with the support I gave with uniform laws on inputs, the output with some level of discretization would look like this for the first neuron, would look like that for the second neuron. And you see that even though I can, of course, discretize in a more accurate manner, the width of the p-boxes will still be pretty wide, right? It doesn't change much the shape of these output states, output p-boxes. It's just a little bit more precise. We'll see why, and we'll see how to counteract this wrapping effect, really. Okay, and that's for the other example with normal laws as inputs. It's just a bit rounded, as you can see. And as I was telling you, once you have these p boxes at the end, you can just look at the probability of some of these linear inequalities you want to interpret just by looking at the corresponding points on the lower and upper CDFs and plausibility and belief functions. So in that application, in this toy example, you'd find the probability that the first output is less than -2 being between 0 and 0.05, and much less nice is the probability for the second output to be greater than 2. It would be found between 0 and 0.59. Not really great. If we had normal, so if we had independent inputs, that's unknown dependency on the left, so the worst case. If we had independent inputs, then we would have a much finer, much more precise p-box as an output, and then the probabilities that our verification problem would be satisfied would be much more tight, right, as you can see. Okay, but still, there's a problem with these focal elements, with these interval focal elements, and that's these classical problems we have in set-based analysis, which is the so-called wrapping effect. Just for the linear layer already, just think of a linear layer which does some kind of rotation by 45 degrees of the initial box, and with some expansion, then you see that it does this transform in orange from this initial box. You'd have, if you want to represent that by interval, to wrap it up into this blue product of intervals, and it widens the intervals all over again. And if you have more layers like that, it will widen again. It won't be very precise. So indeed, we want to change this DSI into something else. And this something else is really to not use intervals, but rather some polytopes, some particular polyhedra that represents multi-dimensional focal elements, right? We're going to go to multi-dimensional focal elements, imprecise probabilities. But we'll use very tractable kinds of polyhedra, which are called zonotops. They are centrosymmetric polytopes, so compact polyhedra with centrosymmetric faces, like this yellow thing here. You see the opposite faces from the center here. And these are encoded as affine images of higher dimensional hypercubes. So here's an example. It's an affine transform on 4 variables, epsilon 1 to epsilon 4, which all belong to -1, 1. In that sense, it's going to give an affine transform of this 4-dimensional hypercube, okay, unit hypercube. And you can check that this gives this yellow picture. So in general, it's given by more generators. So these are these numbers, these vectors 4, -2, 2, 1, and 3, -1. You can see in that example. It would be, defined more formally by this matrix gamma and these generators. Don't let me go into more details for now. The fact is, you can see very easily that these particular parameterization, they're going to be closed under affine transformation. So we're going to be exact on all linear layers, contrarily to what happens with intervals. The only thing is that it will be inexact, or it will have to be an outer approximation when it comes to the nonlinear activation function. So for ReLU, for instance, there's a classical way to interpret the graph of the ReLU between two bounds Lx and Ux with minimal surface, which is a zonotop with few faces. It's this orange zonotop that can be computed with a magical formula that I'm not going to tell you about today. But there's a way to interpret ReLU in a quite tight manner using zonotops, but not exact. And then, of course, so I won't tell you some other thing we've been doing, at least for program analysis, that can be used for neural network analysis as well, which are these probabilistics on top. I'll just right away skip that part and go to these Dempster-Shafer structures on zonotops. How will that work? Pretty easily, at least if I'm just telling you about how to treat independent inputs, right? And then Francesc will tell you more about the case of more complicated copulas, right? Okay, so if you start with independent inputs, it's pretty simple what you should be doing to leverage this VSI sort of analysis to work on zonotopic focal elements. You will still start with an abstraction of this probabilistic constraint input set using this size on each of the different coordinates, right, with a certain number of focal elements. So for instance, in my case, I have 2 inputs and I have these focal elements which are indicated, these intervals, focal elements which are indicated by these vertical lines on the left. And for the other input neuron, you'd have these other focal elements. You'll do the product of these things. So I indicated some of these squares products of these intervals, right? Not all of them. You'll consider them to be zonotops. Cubes in particular are zonotops. And so I signaled out one of these initial cubes or squares. And then you'll propagate these focal elements through the linear layer and nonlinear layer using the zonotopic calculus I've sort of shown you very quickly. So after one step, after one layer, you might produce a real blue zonotop out of this first blue zonotop. Some other zonotop will be an hexagon, which is a projection of a cube, as you can see here. They will overlap, and of course, the probability that the multidimensional CDF would be read as usual. You look at the weights of the focal elements that intersect this lower orthant or quadrant in that case from XY, okay? And so either the ones which are completely included in there or the ones which intersect that quadrant, okay? So in algorithmic form, you'd have this thing, which is just a generalization of what we did with the side. We begin with all these input zonotops, which are just cubes at first, and then we propagate them independently by zonotopic calculi, and then each one of these zonotops that I propagate they will just carry on transport the same weights as they had before, right? I mean, the product of the weights of each DSI they come from originally. So each initial cube has a weight which is the product of all the weights it is the product of. I mean, the weight of the focal elements, it's the product of. Okay, so that's what is indicated here. And then at the end, you can interpret the linear inequality you want to interpret and the CDF on this affine transform on your focal elements, and then find the upper and lower bound of the probability of the probabilities that it's satisfied or not. Okay. So let me just very quickly say a few words about how it goes on actual examples before letting Francesc speak. So it's based on the network on a prototype implementation in Julia. You can take from GitHub. So the toy example, I won't tell you more about it now, but I'll just tell you about the ACAS Xu and this Rockenlander example. So just quickly, indeed, you can see the calculations if you want to test your understanding of what I'm saying in this formal methods conference paper of ours. It fully spelled out the computation on the toy example, and you can see that basically the probability bounds on the properties you need on some of these laws we took in the inputs for the toy example are very tight, and they're computed in very few seconds. And so it's 0.026 seconds for this one, 3 seconds for this one, and it's very comparable to the time it takes to if you were using the naive Dempster-Shafer on intervals structure. Okay, so it's much better than this I. As you can see, the bound is much tighter than this one, and with about the same time to analyze. So just to give you an idea about these problems we're interested in. So the aircraft collision avoidance system, it's a very important thing in our community. It's a collection of 45 DNNs which have 5 inputs, which tell you about the configuration of 2 planes. And the idea of these DNNs is to tell you about, to give you some advisory about what you should be doing to prevent collision between these 2 aircraft. So there are 5 outputs, which are scores of each advisory. The advisories are clear of conflict, you have to do a weak right, a weak left, or a strong right, or a strong left. And we want to check obvious properties about which classification you should get in which conditions. And indeed, so you don't have to read the whole table, but we are, that's our Dempster-Shafer and zonotopes implementation. That's the ProbStar thing I was talking about originally, which is not completely fully guaranteed. You have a level of precision you give, and this sort of exact case in ProbStar is actually just an estimate of the probability that you should get of the properties, as you can see, because here we prove that the probability bounds of these properties are exactly 1, which means that actually it's set theoretically always true, whereas the estimate they give is not quite 1. Okay, so it's not completely guaranteed. Ours is guaranteed. And you can see that the bounds in that case are very similar, except we are guaranteed. And the time it takes to compute them is much less than the time it takes for them to compute these bounds. And also, I must say that these times for ProbStar, it's a case where they parallelized it on 8 cores, whereas our implementation is not parallelized. Okay. And the rocket lander, we have even better analysis results with respect to ProbStar. So it's a typically space, how is it called? A SpaceX kind of, re-entry and landing of a rocket. And you want to prove that the rocket won't tilt on the barge on which it should land. And you can see again that we have even better estimates on the probabilities of properties in far less time than the current state of the art. Okay, so now I'm going to ask Francesc to carry on, and then just tell me when you want to change slides. Thank you.
Okay, well, thank you, Eric. During this first part, I will now be focusing back to the DSI case where the support of the distributions into intervals again, and leave these zonotopes for later. But in all those calculations, something that was required was that either the input variables were independent, in this case the bounds that we obtained were quite tight, or that the dependence was completely unknown. In that case, you just applied the Pifarré bounds and you got quite not tight sets. So the way we have extended this is to try to directly handle dependencies. So that this has two main uses. First, that you can specify multivariate distributions on input, so you just don't need to assume independence between input random variables on the neural network to obtain bounds of safety properties. But also it allows you to track the dependency introduced by the affine layer, since the affine layers mix the inputs of the previous ones in very different ways. They are strongly correlated with each other. So in the original work, these were just handled with unknown dependencies, so the calculations became very broad after the affine layers, while having copulas propagated through the affine transformations as well allow us to keep track of these dependencies, where they come from, and get much tighter bounds. And how we're modeling this is through the use of copulas. So copulas allow us to work sort of separately with the marginal distributions, which will remain specified as DSIs in our case, a discretization of p-boxes, while having a separate structure that allows us to work with how these DSIs depend on each other. And the modeling choice we made here is that the imprecision is all encoded in the marginal. So in the case that Eric said, for example, measuring errors or this kind of data corruptions that can make you lose knowledge on what you're dealing with, that this happens in the marginals, while we take an assumption that the copula between the inputs is known. And this can be either like the independence copula, which is the base case to which we will compare to the other methods, since they only work under independence, but also Gaussian copulas, parametric ones, even empirical copulas, if they are constructed correctly, they would work for this initial modeling. So as before, we have to adapt to operations to propagate copulas and the marginals to the neural networks. And before the operations, how do we relate the marginals and the copulas? So we do it through the copula volume, and it's a quite natural relationship, because in the imprecise marginals, each focal element sort of encompasses a part of the cumulative distribution function of that marginal. So we have an area of the cumulative domain, let's say, that it's defined by quantile levels. So from a marginal DSI, you can get for each focal element the area that it encodes in the cumulative domain given by these quantile levels, and then using these quantile levels, you can evaluate a part of the copula area, which gives you the joint probability that both focal elements happen at the same time in a multivariate sense. So these rectangles that encapsulate the quantile levels defined by the marginals that we evaluate in the form of volume in the copula space will be the way that we jump between marginals and the multivariate distribution during all the calculations here. And now, of course, the first calculation, so the notation will start getting a bit trickier here. But the affine propagation is basically the same as it was in the original work. We just, instead of taking the product of weights, of probability weights for focal elements, we take the volume as we explained in the last slide. So this means that we still have the problem that interval arithmetic is used for the focal elements on they blow up, but we get much tighter probability masses for each focal element. And this, since we're also able to propagate the copulas, these probability masses will stay very tight through all layers, not only in the first one, when dependencies, where we can assume independency. And the more careful step that needs to be done is how to propagate the copula. So we start by a copula between the inputs of a neural network, but after the first affine transformation, we have new variables which have been formed by the affine transformations. And to keep propagating our data through the neural network, we need a new copula to be able to evaluate those new variables in the next layer. How do we propagate it? So we do it sort of introducing memory maps, which map quite naturally the indices, so the intervals, the focal element intervals in the input, which map to each focal element in the output. This works really well because on the interval arithmetic, when you perform an affine transformation of intervals, an interval in each marginal creates an interval in the new variables. So this means that we have a unique correspondent unless we use mergers for computational efficiency, but I won't touch much on that for now. and mapping which intervals in the input variables each interval in the output variable comes from allows to propagate the copula volumes from the input layer to the output layer as well. And with these volumes, we can just do cumulative sums and the quantile levels defined, we can reconstruct a discrete copula between the new variables introduced by the affine transformations. So basically, we first perform the affine transformation on the marginal DSIs, and then we take these memory maps of where each interval comes from in the output variables to reconstruct a discrete copula that we will also propagate with these marginals. We know that since it's a discrete copula in the sense exactness, it's only guaranteed in the quantile levels, but all of the calculations that we have developed keep these quantile levels constant so that we still can get guaranteed bounds without interpolation or other approximations. And after the affine operation, we also have to account for activation functions. This is a bit easier in the case of monotone activation functions that are injective particularly, so ReLU induces a few extra complications. Monotonicity is important because it allows you to just apply them on the focal elements of the interval, so you just apply the activation on both bounds, and if it's monotone, then you're guaranteed to have an outer approximation on the correct outer approximation of the activation applied to that focal element. But in the case of ReLU, there's a couple of problems. The main problem is that since ReLU is not injective, there is a problem in how copulas are determined because it introduces a probability mass for all the elements that are mapped to zero, so all the negative elements before ReLU was applied. And this is even made worse because since we're working with imprecise marginals, we do not know exactly where that degenerate probability mass atom appears in the quantile domain. So to make sure that we do not evaluate anything or construct copulas in the area of the domain that do not remain well defined because they are not unique in that area, we perform a very conservative merger of focal elements. So basically all of the focal elements which interval touches on zero or on the negative side are merged. This gives an outer approximation of the CDFs and the pivots that the DSIs encapsulate, but allow us to continue with the push forward of the copula and ensure that we only evaluate it at places where we know it remains well defined. How do we do that? It's very, so here is the figures that sort of illustrate this merging behavior. On the right hand side, you see how that happens on the marginals. This big new box that appears on the left side, it includes all the focal elements that would go to zero after ReLU. So we just merge them, do a broad over approximation of these marginals. It remains guaranteed because it's a strictly outer approximation. And in the copula domain, on the left side, you can see that a big atom is also introduced on the lower left side, which is a conservative approximation of the area that will also collapse to degenerate after the ReLU operation. And once we can perform this measure, and for any other activation functions, actually, we can also perform a push forward very similarly to how we did with the affine layer, even simpler because we consider just univariate functions. So the notation and the construction is a bit simpler. On the next slide, you'll see the details of it. And it's just basically doing the same, remembering which indices everything came from, which focal elements in before the activation match to which focal elements after it, accounting for the mergers by summing up some extra volumes, but you can still push forward the volumes, the copula volumes previous to the activation functions, and with them reconstruct the copula through cumulative sum of these volumes. So with these two steps, we can basically propagate both marginals and dependence structures, so DSIs and copulas through neural networks. And this gives some interesting results, which we will go back to the toy example. On the next slide, you can see how, so on the left side, you see in the same toy example, that the very simple toy example that Eric touched on before, the marginals that we get for the outputs in the left side when using copulas, and in the right side when not using copulas. And the matrix is a bit distorted, but you obtain much tighter bounds just by carrying out, and this is in both cases assuming independence, but with copulas you can know where that independence came from after the first affine transformation, when that information was lost, when we had no use of copyleft. On the next slide, you can also see that the copyleft that you get in this example, the volumes are not very interpretable with high discretization sizes, but you can get copula contours plotted as well, which can give you some sort of intuition on how the outputs of a network depend on each other, how they are correlated. And there's another example later in which I will offer a bit more insights on how that can be done. And in the next slide, you can see the same table as before, just a bit less content to focus on it. In that, with using DSIs, even with the much more conservative arithmetic of intervals compared to zonotopes, you can get guaranteed probability bounds which are very close to that you obtain with zonotopic arithmetic. It's more expensive in terms of time because a couple of push-forward operations are quite intensive computationally, but this allows to tighten the bounds obtained by just the interval arithmetic quite a lot and make them comparable to zonotopes just by this addition of the copula and how dependencies are induced and conserved through the network. What's the strength of just adding copulas? It first that in the zonotopic arithmetic, activation functions are harder to abstract, while in intervals they are quite natural. So you can naturally account for a lot of activation functions as long as they are monotone and injective. And very easily, so it's applied. It can be applied to more neural networks than just the original method. And then the next case study that I will quickly touch upon is a sigmoid neural network. So you will not be able to so easily verify it with zonotopes. You also recover copulas between each step of the network, but most importantly between the outputs of the network, which can be useful to interpret how outputs depend on each other. And it also allows for evaluating multivariate safety properties. So you can have properties not only on the marginals, linear properties, but also on combinations of the marginals with more precision. The main limitation is the interval arithmetic. So even though the copula helps to offset this wrapping effect that Eric touched upon, is still very conservative arithmetic. And especially for very deep neural networks, these starts to compose on each other and you get very, very conservative approximations due to how intervals blow up in size. The ReLU step is also a very conservative approximation, and we're considering also how we could tighten that while keeping copulas more well-defined. And that the copula push-forward operation is quite expensive computationally, both in terms of memory and operation. So it makes it harder to apply to larger neural networks. On a last quick case study, I'll show you some results. So similarly to the ACAS Xu network that Eric touched upon before, there's a similar system for train control, where you also then want to avoid crashes. And these neural networks have also been used previously for some verification problems in a qualitative way, so either completely guaranteed or not. And here it's a very simple network. It's a single neural network. So this shows how our method also works well for single neural networks, not only the parallel ones. It has just three very simple input variables: the position of the trains. One of them is assumed to be just stopped, and the other one is assumed to be moving at a constant speed. And the property that we will check is whether the trains break or not. And there's some different scenarios on which we check the property. The A and B are just general scenarios, and the safety critical ones are C and D. So in scenario C, the violation of the safety distance is impossible between the trains, so we should expect the networks never to break in that case, or they have no reason to break. While in scenario C, the safety distance is always break. So neural networks should advise to break under the official ETCS rules, which the networks are trained to replicate. On the next slide, you see the results of applying the copula DSI propagation to these neural networks. It's different neural networks all trained for the same task and the same data set, just with increasing complexity. And you can see, so first the safety critical scenarios, you can see that they are all verified. So in a scenario C, so when the crash is impossible, the network never advises the trains to break. While when the safety distance will be violated for sure, there's a bit more uncertainty in that case. So qualitative methods of verification show that this property is not satisfied, so the networks do not always break when the safety distance will be violated for sure. But we can see that they do break with a very high probability. The interpretation of how high the probability should be to avoid a train crash, it's left to whoever would have to approve this. But we obtain much richer information that qualitative methods would be able to obtain, because we say, okay, they do not break with probability 1, but we have bounds on that it does break with very high probability. And what it also, in the next slide, you can see how these bounds broaden a lot when we use imprecise marginals. So in this case, we use imprecise Gaussian random variables where the mean is not known up to ±5. This could be, for instance, when the train position is not known exactly, but there's like only a measurement station every 10 or 5 meters. And you can see that the intervals broaden a lot here, which more further justifies using imprecise probabilities or marginals to account for uncertainty and to obtain guaranteed and robust results, even when you change the modeling assumptions. And so this is also the copulus you get between the outputs. And here is where I wanted to touch just very quickly on how you can use these copulus for interpretation. So especially in scenario A, which is where we apply no constraints on the inputs of the neural network. You can see how in the left-hand side, the copula seems to approach the absolutely positively correlated copula, the upper Frechet bound, while the opposite happens in the other side. That what this suggests is that these networks are seeing a behavior where the left-hand tail of the distribution seem to be positively correlated, what the opposite happens on the right-hand side. So the upper tail is negatively correlated between the two outputs of the network, and the lower one is positively correlated. And there's an area in the middle when this correlation flips from one to the other, and dependencies become harder to determine. And this does change when we change the modeling scenarios as well. So in scenario B, you can still see the same effect, but much weaker and constrained to a much smaller area of the CDF domain, while on scenario C and D, which are the critical safety ones, where the inputs are much more strictly specified, they do seem to behave much more positively correlated in all of the domain. And just to finish, some open problems that remain after this copula extension is, well, we assume that we have unknown marginals, but known dependencies between them, which can be a bit unrealistic. So we're considering whether this framework can be extended to imprecise copulas instead of precise copulas, and how that would affect the propagation. We would also like to consider zonotopic domains for the affine transformations and for the focal elements in general, because they do give us, Eric showed, much more precise arithmetic, which could strengthen the results, especially for very deep neural networks. And to consider how, because we're obtaining a lot of probabilistic information after this propagation, which we are not fully taking advantage of. So we're also considering how to use this probabilistic information for more complex, robust certification or sensitivity analysis between input and output variables. And that also remains an open problem that we're considering. And I think that should be all for my end. So thanks for listening.